Alright, we are going to start, yeah, we're going to do the homework number 5. There's all this beautiful mess. Yeah, we're going to do a fresh one. We're going to do homework 5 straight, blank. I'm going to regret it, but yeah, I did not like homework 5 a lot. But I'm going to do it because it's hard. So, I'm going to do each one step by step. Because yeah, yep, that's what we're gonna do. And I'm gonna try to do my best. Because that's all I can do. Because every time I plug everything to a calculator, it does not like it. But I feel like I'm gonna be lucky. I feel like I'm gonna be lucky and I'm gonna do everything right the first time. Um, I'm hoping I do. But yeah, let's get the problem up on here. So first things first, pull it up in front. We got we got we got this bad boy here. All right. Question wants us to let's not worry about that. We're gonna figure that out. The question wants us to transform it. So first, let's draw this thing. Um, delete all this. I don't need all this on here. Nah. Let's draw all that. Let's draw this. All right. Gotta quickly pause for a second. We got this drawn up here. So we gotta, we need to combine. It wants us to combine. Um, it wants us to do some source transformations. Uh, it wants us to shrink it. We need to shrink it how much? How much are we shrinking? Alright, so we need to shrink this bit here for the first question. We need to shrink all that. That's what we needed to do. So we're going to do that. First, let me do a little trick here. Copy and paste. Get another drawing up that I can fuck with. Alright, we're going to transform this. So how are we going to do that? So, there's one or two ways. We can convert this to a single power source on the left and right. To do that, we do the source transformation to convert this current source transformation. We're going to convert this 8 amp to power. We're going to convert it to power. So we do that by multiplying by the resistor in parallel with it, and then leaving that resistor in series with it. So 8 times 75 is 600. So what we're going to see is, why is this needs to be bigger. Make it bigger. It's a little bit bigger. Great. And what dictates the polarity of the battery is the top arrow of the is the positive. 600 ohms and series was 75. Oops. All right, next step, combine. All right, combine. So we're going to combine these two batteries. They don't have the same polarity, so we're subtracting. But one's greater than the other, so that one's going to dominate. And this should not be in ohms. Let me do reset. Uh, the polarity of this one's going to be plus minus. The other one is plus minus, but it's the other way, not same polarity. So 600 minus 200, what is that? 400. Um, Paste. We're going to erase all this. blah, 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 blah. Stupid thing. 400 plus minus 400 volts. And then we have 200 by adding those two resistors together. Boom. Done. Now we're going to actually attempt to go all the way with this one. The next part, part B, we need to convert. We need to simplify this current stuff we got going on here. So to go to current, we take the resistor that's in series with the power and we divide. So we're gonna get 2 amps pointed up, and then that resistor is gonna be in parallel. We keep the 200 there. That's how we convert. 400 divided by 200, 2 amp. Resistor stays, but it's in parallel now. And that's going to be in parallel with the 800 ohm resistor. And to simplify that, we do 1 over 200 plus 1 over 800 and grab the reciprocal. 1 divided by 0.00625 is 160. Then we get 2 amps and 160. That is a good number. Okay. Now, what do we do? Alright. Next step is we come into a problem here. We have a resistor right here that's 160 ohms. Okay. What do we do? Well, if we want to get to the current source that's across from it right here to add, we're trying to simplify things down. So to go to the next step, we need to create the power and a resistor in series so we can add those two resistors. Right. So we do 2 times 160 gives us our power source. Source transformation, 320 volts. And series with 160, the one that it's in parallel with. And now in series with the other 160. And that's good. And now we have this here. 2 amp. Voila. Now that we're here, we can combine those. The ones in series, and we get 320. And we have a resistor. And blah blah. 320 volt power. So we want to go back to current since we have a current source. We want to simplify it down. So 320 divided by 320 is 1. In parallel with 320. Yep, good stuff. And now that we're back with the current source, now everything's in parallel, we can move stuff around. We can actually add those now, right? 3 amps going up in the same direction, so they're going to be added together. And now that we're at this point, we can draw the rest of the circuit. So we have, I'm already at the bottom of my paper. We got a we got a 320. We got a 320. 320, 480, 128. Any other questions it's asking us? No, we're doing everything right. The next step it's wanting to do is simplify this down further here, which is there in parallel, so you just do 1 over 320 plus 1 over 40. For a, oop, nope, 1 divided by that number, we get into whopping 192. Let's go up here. Get a whopping 192. And blah blah blah. Stupid drawing. That's bad. At least make it look square. With a 128 ohm. Current coming down. I sub O. Alright. Next we are looking for, now it wants to know the current source. So we can do a little current division here if we want to. We have two resistors, and we want to know we want this down here. We want to know the current source going through 128 basically. And we know the current coming in, so we can do 192 total resistance on the bottom. Added that together, divided by the resistor opposite to the one we want, times current is equal to I sub O, which is 1.8. Yep, that's number 1 done. Nice. Let's do number 2. Question number 2. I need to put a bookmark. Bookmark. 1220. Alright. 1220, we finished 1. We finished 1. Alright, now we're doing 2. We need to do 2. Alright. This one's actually super easy, which is nice. I can even do it right here in this little corner. Put it simply, the question states, pull it up, number 2. A real voltage source is modeled as a 3.5 ideal voltage source in series with a 2.2 k ohm resistance. This circuit is now transformed into an ideal current source in parallel. What is the resistance? Okay, so we have a real voltage source, and it's in series with a resistor. Alright, so if we convert this into, we do a source transformation to a current in parallel with a resistor, that resistor value does not change because the transformation is voltage divided by resistance gives us our current, and then we put the resistor in parallel with that current, so the value doesn't change, which is 2.2 here, like it says. Number 3, we're going to be dealing with some numbers, sadly. So we were dealing with this here, this figure, and we need to figure out, find the power dissipated by the 160 ohm resistor. You can see the answer there. Yeah, you're gonna have different numbers though for the next two, so it'd be nice if you learned how to do. This is mostly source transformations you can do for this one, which is nice. Um, and let's do that. Let's switch to the old iPad. Alright, so we are going to draw it real quick. Let me pause real quick. Alright, we're back. So, our goal is to find the power dissipated by this 160 ohm resistor. Alright. So, good news. We have a lot of things in parallel. So, we can do some, we have some power sources here that are in series with some resistors. We can do some source transformations here and here. We could also do a giant mesh analysis, but that would be a pain in the ass. This question is clearly made so that you could do a nice, easy source transformation. So we're going to do that. Okay. So let's do that. Alright, so what we're going to do first is I'm going to copy this. Copy, paste, come up here. Alright. And now I'm going to convert both of these into, ooh, what's the voltage there? I didn't write that. The voltage there is 15. 15. Okay. So let's run some numbers. Okay. 7.5 divided by 500 is going to be our current for the first one, which is 0.015. We can convert that to milliamps since that's clearly what the problem is keeping the currents in. So the polarity had the plus on the bottom, so we're going to have an arrow pointing down. 15 milliamps in parallel with that resistor. That's 500. We're going to do the same here. Erase that. It's getting a little tight. Let me move this over. It's getting a little tight. Let me move that over. Okay, so we need 15 divided by 600. 15 divided by 600. That is 25. Point 0.025. It's going to be 25 milliamps. Pointing to the top, because the plus is on the top. 25 milliamps. In parallel with 600 ohms. Connect. Connect. Alright, now we can do a lot of simplification. All these currents, let's add them all together. 10 minus 15 plus 25. So we'll do 25 first as it's easier. 25 minus 15 is 10. 10 plus 10 is 20. So these two that are pointing up will cancel out with this middle one here. We'll get 20 milliamps. And then we have three resistors in parallel. The 2K1, the 500, and the 600. Let's combine all those right now. So let's do 1 over 2000 plus 1 over 500. I think we can do 3 in a row. I'll try it and see if we get a good number. And then invert all of this once it's done. So let's plug that into a calculator. Get 240. That's a nice number. So this is all in parallel with 240 simplified. Let's get rid of these. Move it away. Okay. Alright, so now what we have is here, we have 160. 400. And we have the 1K down here. Alright. And our goal is to find what the power dissipated is at 160. So this current and this resistor that's in parallel with it are kind of in the way. So what we can do is we can Let's do a source transformation. That's what we're gonna do. We're gonna do a source transformation. And yeah, yeah. We'll do a source transformation. We'll do 20.020 times 240 because it was a voltage of 4.8, and that's going to be in series with a 240 and 160. And one thing we can do here is, you see these two resistors are in parallel, so we can simplify that because we want a single circuit so that we can do a nice KVL. That gives us we get not a nice number, but it's the right number. 285.714. Alright, so what do we do now? We want to know power dissipated here. So, a nice thing is we know that power is equal to resistance times I squared. And we can figure out the current here, because we know all the resistors that are in series, which can be added up together to give us the total resistance. And we can take that total resistance and put it under the voltage. 4.8 voltage divided by R is equal to I. 4.8 divided by 240 plus 160 plus 285.714. And then my calculator. 240, write that down for anyone visual. Over 4.8 gives us the current that we want, which is 0.007 amps. Alright, let's plug that into our equation. 0.007 squared times 160 gives us 0.00784, which is equal to 7.84 milliwatts. Let's bookmark that. Alright, and yeah, that's number 3. Number 4 is harder and longer. 23, 30. Done. Alright, I'm trying to bookmark these. Suggestion through Trey. Alright, so first question. Use the principle of superposition to find V naught in the circuit figure 1. V sub S is equal to 80 and I sub S is equal to 7.5. Okay, so what we're going to need to do is look at the circuit first. Alright, so we need to find V naught, which is here, the voltage across that 4 ohm resistor. And it wants us to use superposition to solve it. So we're going to short circuit this here first, and then make an open circuit here at I sub S. Yeah, that is what we're going to do. Yep. And that's how we're going to solve the problem. So that's going to be our approach. That's how we do superposition. And we're gonna do some nodal analysis probably with it, and maybe some meshes. I doubt mesh. Probably nodal. Nodal is a little bit faster for this, but it's your calculator doesn't like to do it a lot. Let me draw this really quick. Alright, we have our figure drawn up here for the most part. Boop. We're going to do some copy and pasting because I'm going to have to modify it a little. We're going to make 3 of them. I know everybody doesn't have an iPad, but it's nice. Separate them because there's going to be some nodal analysis underneath them probably. Alright. So that's original. We're going to do solve for 1 with killing one of the sources. To note, the dependent current source there, because it's not a definite source, like it's not known and it's not dependent, it's independent because it's changing. It'll change as you pick which current source you kill. It you don't ever kill it by itself. You don't it just stays there the whole time. Like like I'll do in the problems. So first we're gonna kill or get rid of current. And when you kill current, you create an open circuit. You just leave it open like so. And basically there's just nothing there. Yeah. Look at that circuit side never existed kind of deal. So we're just gonna do A and B. I'll label them like it's pretty easy to label them like this. So we have A and B as the nodes, and then we're gonna ground here. And by grounding, if y'all don't know this yet, you pick one source to ground, and everything connected to it is ground, so that you'll have A. In theory, when you do your nodal analysis, you'll do A, your source, minus whatever power's opposing it, and since it's ground, it's 0, so you have A divided by 8. That's basically what we're doing, but you're supposed to, in theory, you're grounding it, the one other node you're not using, which is usually the bottom. And I'll solve it like so. So, we'll do A first. So, the we're doing a KCL, basically is what it is. So, the KCL for all the currents entering A are going to be A minus 80, which is divided by 6, which is that first current, plus A divided by 8, plus A minus B, 2. You notice how when we're doing A, we're doing like with respect to A for the first one kind of deal. And then we have that top current, the independent current source, dependent, independent? I think it's independent. I don't know. Minus the variable I sub 1 will be, I'll just find that real quick. So I sub 1 is aiming to the right. Now the current going to the right is going to be equal to, in the direction going to the right, 80 minus A divided by 6, which is the voltage drop on top divided by resistance, which is current. It's basically all the KCL nodal analysis stuff is. So it's kind of a reverse of this first one we did. So basically this first one is negative I sub 1 in theory. So 80 minus A divided by 6. And that's all of them equal to 0. This is for A. Nodal analysis. Now let's do B. And first one, B going to 4. B is going to ground, so it's just B on top. Plus B minus A, respect to B, divided by 2, plus, it's plus because the current is going away from B, so it's going to be 3 times, we already have what I sub 1 is, up top here, 80 minus A divided by 6, equal to 0. Now, these are your numbers that you should get, and we can make it look nicer if we really wanted to. I don't usually do that, but I will now. I will do that since I'm trying to do a good job. Usually I'll try to wing it and put them in right here. It kind of looks nasty, but that's what it is. So A, we'll put a nicer version of it. We'll factor out the A, and we'll have 1 over 6 plus 1 over 8 plus 1 over 2, and then we have this A here. Negative 3 times negative 1 is positive 3. 3 divided by 6 is 1/2. That's all our A's. And the only B we have is this one here, which is negative 1/2. And we have two constants, here and here. Negative 80 divided by 6, and we'll add negative 3 times 80 divided by 6 will be our two constants. Now notice how they're both negative, so they're going to be positive when we add them to the other side. So we'll do 80 divided by 6 plus 3 times 80, which is 240, divided by 6. We get 53.33333333. Repeating. And then we'll do B. What question is this, by the way? This is 4, right? There's only one more after this. Yeah. This is a little bit, it's a little bit painful. Alright. Yeah, we do A first. We want to keep our system of equations in order. So we have first one, negative 1/2 plus 3 times negative 1 is a negative 1/2 plus B, got 1/4 plus 1/2, 1, 2, 1, 2, okay. And then we have 3 times 80 divided by 6. We're subtracting that over, so we're going to have a negative constant. So 240 divided by 6, 40, but it's negative on the other side. And we'll plug this into our calculator real quick, and we get, alright, so for A we get, my calculator was wrong for like a second, I just put one number in wrong, 42.666, and B is equal to 3.55. Alright, well, that's one part done. Now I have to do it with killing the other source. Yay. This is so fun. Alright. Copy. I'm gonna go to bed after this. Alright, let's do this and then paste. Alright, stay there. We are now going to short the voltage source. Voila, we shorted it. Okay. Nodal analysis. This can be A and this will be B. And then we'll ground this and everything connected to it, noted. So that whole thing becomes grounded now. Wow. Okay. So now let's do a nodal analysis. A is going to be A divided by 6. We're going to go faster now since we already did it once. Plus A minus B divided by 2. Current coming in is that one ooh, that doesn't look, what a 3I1. That's, and I1 in this equation is equal to, A is going this way, so it's negative A is equal to I sub 1. So 3, negative A. And that is our system of equations for A. And then we'll do B is equal to minus that current coming in, plus B over 4, plus B minus A over that 2 ohm resistor, plus that one current up top, which is going to be 3, negative A, which is I1, is equal to 0. Okay. We'll write a nicer system of equations here. Factor out the A. 1 over 6 plus 1 over 8 plus 1 half. Negative 3 times negative A is positive 3A. Ah, I see where I messed up. 3A? No. Current is not just voltage. Negative A divided by 6. That's my first mistake. I was wondering why. Now we have current. I1 is a current. And that's what we got. Okay. So, yeah. negative 3 times negative 1 is positive 3, so it's 1 half. And B is just negative 1 half. It looks a lot like the first one, to be honest. But there's no constant on the right. And B is equal to, that negative 7.5 will be a 7.5 on the right. A, factor out the A first. Negative 1 half plus negative 1/6. That's it. Plus B, 1/4 plus 1 half. And yeah, that's it. That's our system of equations. And I'm going to check my answer real quick. No, I don't know why I put negative 1/6 here. This is 3 times negative 1/6. So that's going to be a negative 1 half. And it's exactly like the other equation. Yep. Okay. Except this is 0, and that one's 7.5. And we get a whopping 8. A is equal to A, and B is equal to 20.666. At least I'm catching my mistakes more now. That's good. And to find the final superposition, we add the 2 points together. So we want to know the voltage going across the 4 amp resistor. So B, the voltage we've been finding at that node above it, will be the voltage going across it. So it's going to be 20.66 plus 3.55, and we get 0.66 plus 3.55. You get 24.21, which is close enough to your answer. It should have been. Yeah, that's really close. The answer is 24.2, but that'll get you the answer. Bolts. Woo! First part done, and that's painful. Mm. Not sure if I want to do the second part, to be honest, but I will. I'm gonna become a demon after this, hopefully. Alright. So this is our second figure. This here. This bad boy. Voltage 20. Current's 8.7. And we need to find the voltage V across that 10 ohm resistor we see down there. We see there's an independent voltage source. That's going to be a little bit of a hassle, but we will get it. It will be fine. It will be fine. Okay. Hold on. Ooh, let me draw this. Alright, we're back. We're gonna do this problem here. We're gonna do this circuit, and we need to find V across this 10 ohm resistor right here. Right there in the middle. So we're gonna do that, and we're given V and I for the two main current sources. So we are gonna do that. I'm gonna draw it real quick. Alright, we drew the circuit. We're going to eliminate the current first. So it's like this. And we can do two nodes, A and B. Alright, we can ground this down here. Okay, let's do a nodal analysis for A. So we have 2.5 and 7.5 going down. So that's going to be 8 divided by 10 going to ground. And we have plus another 8 over 10. Now we have a super node with the independent or dependent on something, blah blah blah, uh, variable current source or voltage source. Well, the current going through here is I sub x in this case. So it's going to be minus 8 over 10. But it's pretty cold outside. Since it's a super node, we have to give an equation for it. I sub x is equal to 8 over 10. A over 10 is equal to B minus A, like so. Now we can do the rest. Now we'll treat it as one whole KCL, going 1, 2, 3, and 4. So we'll have plus B divided by 2.5 plus b minus 20 divided by 1 equal to 0. So we have two equations, this one, two unknowns, a and b. So we'll have a 1 over 10 plus 1 over 10, that's that, plus b 1 over 2.5 plus 1, constant negative 20, add that over is 20. We have our first equation. And now for our second one, we don't really want that variable a on the b on the left, so we're going to subtract it over. So we have b minus a minus 8a over 10 is equal to 0. So we'll have a b. Alright, I'm back. Alright, then we're going to write a second equation for this one up there. So a is negative 1 plus negative 1 over 10 plus b, which is just 1, is equal to 0. Now let's plug this into our calculator and see what we get. Hopefully we get some good numbers. Good numbers, please. Please bless me with good numbers. So 1 over 10 plus 1 over 10, basically 2 over 10. And then 1 divided by 2.5 plus 1. And we have negative 1 plus negative 1 divided by, which negative 1.1, but whatever, in 1. And b is 20 and 0. A raised to negative 1 times b, and we get a good number. I think this is a good number. We'll see if it's right in the end. We get a is 11.49, and we get b is equal to 12.64. Doesn't look too bad. It's just depends on our second one how it turns out. I think we'll get close. We killed the current source in the first one, so we're going to kill the voltage in this one. We're going to short circuit it. And shorted. Alright. Now we are going to do nodal analysis. I like nodal analysis, to be honest with you. We're going to ground this whole thing that's connected. Grounded. Alright. And we have 1, 2, 3 essential nodes that we're looking at. Okay. Alright. Yeah. We're going to do A first. A is equal to negative 8.7, because that current's coming in, plus A divided by 7.5, plus A minus B divided by 2.5. B. We'll do B next. We have B and C are a supernode. We see that. So let's first get the equation for our source there. I sub x is going to be equal to A divided by 7.5. So we have A divided by 7.5 is equal to C minus B. And what determines C minus B is C is on the plus side, B is on the minus side of the signs. So B will be the one on the right. Subtracted. C minus B. C is positive, B is negative. We don't like this. A is there. We have an unsolved constant. We're gonna pull it over. We'll have C minus B minus A over 7.5 is equal to 0. Now that's gonna be our second equation. Now let's do our super node here, which is gonna be B and C, the mixture of the two. We're gonna do B minus A divided by 2.5 plus B over 10, alright, plus C over 2.5 plus C over 1. Alright, so we have these numbers equal to 0. No constants for that one. Now let's make it look nice and pretty. So we're gonna have we're gonna do A first, simplify it, or make it look nice, equal to 0. We can plus that 8.7 over, and we'll get that. And then we're gonna have A, factor out the A, and we're gonna have 1 over 7.5. Oh, that's nastily close to everything. Okay. 1, factor out the A, over 7.5 plus 1 over 2.5 plus B, which is negative 1 over 2.5. There we go. And then we're going to do the supernode B and C. We're going to do A first. Oh, notes. Because we have C's unknown. Do we know C? No, we don't know C. We don't know C, so we have to do plus C, which is 0. Alright. A, we're doing B and C, the supernode. A, factor out the A. We have negative 1 over 2.5 is the first one. Plus, there's nothing else, so we'll stop there. Plus B, factor out the B. 1 over 2.5, 2.5 plus 1 over 10. That's it. Plus C, factor out the C. 0.5 plus 1. No constants that we have to worry about. And now let's bring that nodal equation down. We have is equal to 0. This is like the supernode. The supernode is going to be A, which is just negative 1 over 7.5 plus B, which is just going to be negative 1 plus C, which is just going to be 1 equal to 0, and that's it. So we're going to have a 3 by 3 matrix, and we're going to get 1 divided by 7.5 plus 1 divided by 2.5 for the first one, negative 1 divided by 2.5 for the second, 0 for C, negative 1 divided by 2.5 for the second row first column, 1 divided by 2.5 plus 1 divided by 10 for B for the second column, and then for C for the second column is going to be 1 divided by 2.5 plus 1. Now for the supernode, the last one we'll have A is negative 1 divided by 7.5. B is negative 1. C is 1. Our constants, we'll have 3 of them. We have 8.7, 0, 8.7, and 0 and 0. A raised to the negative 1 times B. And we get a good number, I feel like. So if A is equal to 17.8125, B is equal to 2, and C is equal to 4.375. Right on. So what is B in our equation? Well, B is what we want. B is where V is, what we're trying to find. We're trying to find the voltage going across there. And our A in the first one is what we want because that's the voltage going across. So we're going to have 11.49 plus our B, which is 2, and we get 13.49, which is exactly the number we wanted. Nice. Volts. It's exactly the right number we want. Nice. That's some good work there. All right. Now we're going to the next one. Okay. So for our last one, this is the last one. It's this here. We want to find the V naught there. Now it's good to note. This V naught is connected to here and here. Wait. So what's stopping us from erasing these lines? Because there's nothing that's gonna flow through here. Hold on. Alright. So what I was saying was basically what's stopping us from putting V naught at this 20 ohm resistor? There's nothing, really. The voltage across there is going to be the same as V naught. But by theory, nothing can really go to these points. This is the answer, but we're going to get to that. Alright, I'm going to draw this really quick and then pull it up, and we're going to solve it for V naught. And it wants us to use what? Superposition? Yeah, I hate that shit, but we're going to do it. So, yeah, one sec. Alright, so we have this crooked ass circuit I drew. I'm gonna make a few more because we're gonna have to do some erasing. Copy, paste, paste. Move all this shit there over to a good spot. Get it sorted nice. Alright. So, we're given the voltage as 45 volts here. 45. This fucking mic. 45 volts. And this is going to be 7 milliamps. Okay. So we are going to do some nodal analysis. Excuse me. Alright. So we are going to first, I didn't have this shit drawn on any of them. We're going to first eliminate the current source, right? We're going to eliminate the current source because we're doing superposition. Eliminate this one. It's just going to be an open circuit. Nothing's going to flow through it. It's going to be nice. Nice stuff. We're going to ground here. Okay. So, good news. Good news. This node here is going to be 45 too. Because going to ground is 0. And since the power is right here is at ground, it has no other path to go but to here at this node. So, it's going to be 100% 45 of that node. We'll call it node A. A is 45. And then we're going to call this whole area over here B. B has a lot of unknowns. But we know that the current going for I, we want to solve for this unknown variable current source up top. You solve for this here because it needs that. And that's going to be equal to, since it's going to the left, B minus 45, that voltage on top, divided by resistance is current. 4,000. That is what that is. So now we can solve for B. B is going to be equal to B divided by 20,000 going to ground plus B, the KC on the left, minus 45 divided by 4,000. And then we're going to have plus, no, it's going to be minus that current coming in, minus 2.2 RB minus 45 over 4,000. It's equal to 0. Notice how these are the same variables. We could substitute them in. Even x is equal to b minus 45 divided by 4,000, and then we can combine them. So we can combine them in general. So what's 1 plus negative 2.2? We get negative 1.2. b minus 45 divided by 4,000 equal to 0. B divided by 20,000. We could have let them be, but it's nice to have it simplified down. It's nice. So we can solve for B now. We can find B. And B will be, see what I did there? 1, 1, 1, changing my, so if you want to do it, you could put this into your calculator, your matrix calculator. It'll just be a little 1 by 1. So B will be 1 over 20,000. I'm not going to sort it too much because we don't have a lot of work to do. Minus 1.2 divided by 4,000. And we have B being negative 0.00025. And then our constant is going to be negative 1.2 times that 45 there. And that's going to be a positive. And it'll be negative when we make it a constant on the right. So what is going to be that number? It's going to be negative 1.2. It's going to be negative no matter what. We know that, times 45 divided by 4,000. Negative 0.0135. And we get 54. B is equal to 54 volts. That's our first voltage. Now we need to find the second by eliminating the power. We're going to short circuit it. Now this whole thing will be grounded. And we just have another one single node. We'll call it node A. And we're going to solve for node A. So we can first solve for this unknown variable I sub whatever, and we can set it equal to, since it's going to the left, it's going with A, as A goes to ground, so it's going to be A divided by 4,000. Nice. So now we can do the whole analysis now. So we have negative, that current coming into A, which makes it negative, 2.2 A over 4,000 plus A over 4,000. We have another scenario like we did the last one. Plus the current, right? We'll keep it in its actual value, 0.07 amps. We don't have to put the unit, so. And then plus A over 20,000 equal to 0. We can add these together. We'll get negative 1.2 A over 4,000 plus 0.007 plus A over 20,000 is equal to 0. So our constant is, you see, is right here. Negative 0.007 is going to be our constant for our other matrix. And for A, we're going to have negative 1.2 divided by 4,000 plus 1 divided by 20,000. Second, quit A raised to the negative 1 times B. We get 28. So 54 plus 28 is 6. Carry the 1. 62 plus 20 is 82 volts. Final answer. And yeah, that was that. Love this stuff.